And there we go. Okay, so we're going to pick up with the second part of section 3.1. Part B or part 2. I think on the syllabus, I call it B. And we're going to look at our number system. So our number system is actually a Hindu Arabic numeration system. So our number system, we actually can credit to Hindu and Arabic mathematicians who came up with this system of writing numbers. So we use the digits 0 through 9. So we have 10 digits that we use. Our number system is base 10. And depending on where the digit is, it is representing a specific place value. So this has to do with our place value system. Let me just give you an example. So let's say I give you the number 527. Okay, so place value wise, 5 happens to be, because we're base 10, it's in the 10 squared place, 10 squared. And 2 is in the 10 to the 1. And 7 is in the 10 to the 0. So we translate 10 squared to be really just 100. And 10 to the 1 is just 10. And then 10 to the 0 is actually 1. So this is the hundreds place, tens place, and ones place. And we know those words. We're going to review them, okay? The place values, actual words, but it's all powers of 10. So if I add any extra numbers, if I add any more numbers to the front, I'm basically adding powers of 10 each time. By the way, the number system written like this, written in this form, is often called expanded form. And they typically, when they write something in expanded form, it really looks like this, rather than just a column like how I have it written. It's 5 times 100 plus 2 times 10 plus 7 times 1. That's kind of what they call expanded form. And of course, we know that if we were to literally multiply those out, it becomes 500 plus 20 plus 7, which is our original number when we work it all the way through. So they do have this kind of idea called expanded form. Now, in other number systems, it works very similarly. So last time I think we had seen the Babylonian number system, and the Babylonian number system, let me see, was that one 20? Babylonian. Okay, no, yes. No, Babylonian is 60, base 60. So base 60 means if I had written 527, but I actually want it base 60, we use this little subscript notation to represent that. So when you see a number, and that just like looks terribly written, I'm sorry, that 5 is kind of sad. Let me write it a little bit cleaner. 5, 2, 7. I don't know if that was much better. If it has like a small word that says a number, like if I had written 60, that means I'm looking at the number 527 in the base 60 number system. And just looking at what we kind of did above, that means 5 times 60 squared, 2 times 60 to the 1, and 7 times 60 to the 0. And then we could figure out what each of those are, what 60 squared is, what 60 to the 1 is, and 60 to the 0 is 1, that's the ones place. And figure out what the number is then in base 10. But that's what it means when you're talking about something in base 60. So let's just do a nicer number system, smaller number system. Like let's say 527 in the base 5 number system. Okay. That means if I wanted to know what that is in our number system, what does 527 represent in base 5 number system? What is that for us if it was in our number system? I could work out 5 times 5 squared, 2 times 5 to the 1, and 7 times 5 to the 0. Okay, so 5 squared. That's a 1. That's kind of a sad looking one. Okay, that's 25. 5 times 25. That's just 2 times 5. And that's a 1. So 5 times 25, that's 5 quarters, which is 125. 2 times 5 is 10. And then 7. Okay, so here, if I add that all up, and we're going to talk about adding in the next section. But if you use the calculator, that's fine. You can add it up really quick. So 135 plus 7 is 142. Okay, so in our number system, 527 base 5 is worth 142 in our number system. Okay, that's how we kind of look at base 5 number system versus our number system. Okay, so there we have it kind of set up in different number systems. Now I want to come back to place value here. And in particular, I want to just go back over our place values in our number system. So let me give a very exaggerated number. Let's look at the number 3, 2, 5, 7, 8, 6, 1, 9. Okay, so there's a number. And place value wise, the 9 here at the beginning would be in the ones place. And here, I'm going to turn this to the side and hopefully I don't mess it all up. That's the ones place. You know what? Here, I'll do it kind of diagonal so you can kind of read it while still staring at the screen. So that's the ones place. This 1, the number, the digit 1, is in the tens place, which is 10 to the 1. 6 is in the hundreds place. So sloppy. Hundreds place. It's really hard trying to write without touching the screen and bumping it all over the place. 8 is in the thousands place. 7 is in the 10,000s place. 5 is in the 100,000s place. 2 jumps into the millions. And then we kind of repeat the pattern we just saw. Then it's 10 millions. And then it would go 100 million and then move into the billions and so forth. Okay, so that's our number, our place value. And if I wanted to write this number out in words, I would need these place values to do it. Give myself a little space here. So this is the number. We base it on the commas typically. So because 32 is in front of the first comma, I'm using the last digit based on the comma. So these all represent in this comma things that are in the millions category, right? 1 million, 10 million, or 100 million. So we would say 32 million. And then the next group is the thousands place. So then we would say 500 and 578. I'm gonna run out of space, so I'll have to go down here. 78,000. And then the last number would be 619. So we use place value when we write words out. We also need place value when we're talking about rounding numbers. So we need to have an understanding of place value when we want to round something. So let's say, for instance, let me get the number. Let's do 5, 2, 3, 4, 6. Actually, here, let's do 7, 4, 6. Make it a little more interesting that way. Okay, so the rule with rounding is if you need to locate the number in the place value you're rounding to. Okay, so for this particular problem, let's say I'd like to round to the hundreds place. All right, so that number would be the 7. The 7 is in the hundreds place. You can look above just to make sure. Cool. Yep, third one, 7, hundreds. Okay, so we look at that number. And then what we want to do when you're rounding, the idea is to eliminate some of the numbers because it's cumbersome for our brain to remember. So it's easier for our brain to think of a number with more zeros. It's just easier for our brain to calculate and retain. So what I'm interested in is figuring out if I should be thinking of this as being 52,700, adding zeros after, or don't write this down. This is me kind of going through the thought process. 52,800. So what I'm trying to determine is if this particular number, if it's closer to this one or this one. And to do that, to figure that out, we look at the number next to the 7. Sorry, I don't want to say 7 because I'm trying to write this in general. So look at the number next to place value number. Okay. If that number, which in this case, in our problem, the number next to the 7 would be the 4 here. If that number is 5 or higher, that means we believe that this overall number needs to be rounded up. Then round up. In other words, we would be saying that 52,746 is closer to this one if the number next to the 7 is 5 or higher. In this case, though, it happens not to be. It falls into the other category. If it's 4 or lower, then leave the number the same. So in this case, it is 4 or lower. So that would be this category. We're saying it's closer in value to 52,700. So this is the final answer, the 52,700, because the number next to 7 is 4 or lower. Therefore, we write it as a 7 and then add zeros after the fact. Let's try that again. Let's round then the thousands place. So this time, the number I'm looking at, erase all my extras here, I'd be looking at the 2. And next to the 2, I see that the number is 7. That would qualify in this category of 5 or higher. So I'm going to round the number. Oops, not the 7, the 2. I'm going to round the number up to 53, or 3, I should say, and then add zeros after that moment. So I'm saying that 52,746 is closer to 53,000 than it is to 52,000. Okay. So the process of rounding is kind of figuring out the value it's close to. And a lot of people who do like grocery shopping kind of have a general understanding, right? If you're grocery shopping and you want to kind of make sure you're within your budget, and let's say you pick up a few items. Let's say one item costs $5.99. This one is $1.25. And then you got, I don't know, let's say an item for 11, 60, something like that. All right. What we typically do is just kind of quickly round them in our head. And we're like, okay, $5.99, that's close to $6. 125, let's just call that $1. It's closer to $1 than it is to $2. Okay. And then 11.60, that's 12 bucks. And so we could kind of add those up in our head and we're like, boom, $19. That's an estimate, a rough estimate. That's how rounding kind of works. Now, some people, because they want to maybe they'd rather have an overestimate, okay, just to make sure they're within their means, they would always round up. That's something we'll talk about later on. But in rounding in general, we kind of use the idea that if the number is 5 or higher, we round up. So looking here, I'm looking at the number next to it. Since it's a 9, I rounded the 5 up to 6. And I'm kind of neglecting the fact that it's $6, right? There's the zeros there. Looking at the 1, I looked at the number next to it and I'm like, okay, that's lower than 5. So I'm going to leave it at $1. And then the 11.60, I'm looking here at the 1, but looking at the 6, that's 5 or higher. So I rounded up to 12. All right. So we kind of have a general understanding of this anyways in our daily life, but we do have different ways of rounding. But the traditional rounding is you look at the number next to it, and if it's 5 or higher, you're rounding it up. If it's 4 or lower, you're leaving it the same. And then we're introducing zeros because 0 makes our life much easier. All right. So let's talk about how we can visualize numbers, which they call models for numeration. So we're visualizing our numbers now. And really the one we're going to most use is the base 10 system. But especially when you're working with children, we could kind of use anything we want, right? When you start talking about numbers, a lot of people will use shapes to use for an idea of representing 5, and they like grab 5 apples and they're like, this represents 5. Or if you get 5 carrots, that represents 5. So we can use kind of different models to do that. One of the models the book likes to introduce is called the bundle of sticks model. So the way they do this is it uses sticks, a single stick. And here I'm going to draw my stick as a red stick. So I'll just be really boring and just draw kind of a cylinder. There's my stick. A single stick is representing a 1. A single item. Okay. If I bunch or bundle 10 of these, oops, this is going to be very annoying to draw, but it's okay. Bear with me. It'll get better. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. There's 10 of them. Okay. So this represents 10 sticks. And they like to put like a little tie off around them. Boop. Okay. That's a bundle of 10. Now for us, because I'm not going to draw that every single time, that was super annoying for me to do. I'm going to draw it as a big, boop, giant cylinder. That's my big bundle of 10. Okay. My big bundle of 10. And then I could bundle 10 of these bundles. I could have 10 of them, and that would represent 100. It's rare, but it does exist. Now, here's how we could use the bundle of sticks model to represent a number. Let's say I want to draw out the number 34. So using the bundle of sticks model, I would get these cylinder bundles here. I need 3 of them to represent 3 in the tens place. And then I need 4 single sticks to represent 4 in the ones place. So these are how many are in the tens place, and these are in the ones place. And there you go. That would represent the number 30 and 4. And really, those bundles are supposed to have 10 sticks each. So if I were to break up all the bundles, I would literally have 34 individual sticks. But it's much quicker to think of it in bundles like this. Okay. The other common system used is the base 10 grid. Okay, so here, let me pause for a second. Ugh, sorry, and this is gonna take me a second. I apologize. I wish it was so much smoother. And I'm gonna turn my video back on. There we go. Okay, so for our textbook, the publisher actually provided a base 10 grid system, which I went ahead and linked in Canvas for you if you want to use this like on your homework, because it might make your life easier. I don't know. We'll see. I have another system I might use, or we can kind of cheat and use a system similar to what we just talked about. And you could like literally cut these out like this. I just printed another one, cut it out. And so you can like use these on your homework if you want to for visualizing. We'll use those a little bit more when we get into decimals, but that's next term. But that's one way we could kind of use that number system. Let me share this on my screen. I have one I have created in Word that uses the base 10 squares. Here, let me scroll. There we go. Okay, so clearly the little single square is a ones. Wow, I'm going to try to draw on this, and it's going to be so bad. Here, let me turn my video off again. You let me, there we go. Thank you. So this is the ones. This would be tens, and this would be hundreds. And literally we have 100 squares there. Okay. And I can use this to help me represent the numbers using our base 10 number system. So I'm going to go ahead and I'm going to literally grab from here. It's like not wanting to let me erase. There we go. Grab from here and use it to do a representation. So I'll cheat a little bit, and then I'm going to stop cheating. I'm going to go to ghetto. Okay. So I'm going to do fancy and then ghetto. Okay, so let's say I wanted to represent the number 250. The base 10 numbers. The way I have to do that is I would need 2 of the large squares. So I'm off screen. I'm going to the number system here. I'm grabbing the picture, and I'm going to go back to the screen. Hopefully that worked. And I'm going to paste that in. Yeah, I know. There we go. Haha, there we go. 1 of the base 100. So that represents 100 all on its own. And if I put another one in, boom, there's 2 of them. All right. So now I have the 2 from in the hundreds place. Okay. And now I need to go grab, and I would need to do 5 of those. Okay. So just gonna boop. 1, 2, 3, 4, and 5. All right. And then to represent the single ones, I would need to grab those little squares, and I would need 3 of them. Let me grab. All right, back in here. Okay. Just scooch over a bit. Okay, 1. Be able to paste over here. Yes, 2. Come on. Thank you. And 3. Boom. And there we go. Doesn't really matter how we organize them, but we have 2 100s, 2 representing hundreds, 5 of them representing tens, and then ones place, 3 of them in the ones place. And that's how we could visually represent 253. Okay, so let's say this kind of visualization works with other base number systems. Now, really quickly, they give a name to each of these. I'm going to go ahead and reshare the other document. Sorry, because I wanted to label that. So I called that the ones, the tens, and the hundreds. But what they really call them in the book for labels is they call this the units, the longs, and the flats. They just do that for referencing. So when they said, let me go back to our problem, our example that we had, 253, that could be represented by 2 flats, 5 longs, and 3 units. And that's a verbal way of saying the visualization that we have these 2 10 by 10 grids, 3 10 square stacks, and 5 10 square stacks, and 3 single little boxes, single little squares. Okay, so let's say I have a number like, I'll give myself a smaller number. How about 39? All right, 39. And let's say I want to represent 39 with base 5. With base 5 pieces. So I wouldn't have a 10 by 10 grid anymore. My grid would now be 5 by 5. So 5 rows, 1, 2, 3, 4, 5, pretending those were all perfect. 5 columns, 1, 2, 3, 4, 5. So that's a 5 by 5 or 25. Then I could do my longs. So that's my flats. My flats are 5 by 5s. My longs would only have 5, 1, 2, 3, 4, 5 squares in them. And then my little squares are still counting as little squares, ones each. Okay, each one's places. Okay, so at the moment, what I have here is a 25 and a 5. That adds up to 30. And I want to represent 39, right? 39. So I need then to have another 5 here, because that'll be 35. 2, 3, 4, 5. So another 5. Oh, did I do 5? Yeah, I did. So that adds up to 35. And then I would need 4 of these little squares. And that should give me 39 when I add all these numbers together. Visually, 39 little individual squares. But what's really cool about this, I'm going to write it in their little flats and longs language. I have 1 flat, 2 longs, and 4 units. So in base 5, this is the number 1, 2, 4 in base 5. So the number 39 in base 5 is 1, 2, 4. So you could use this kind of visualization technique to convert between the base 5 or any base number system into our number system and vice versa. It's kind of a nifty way of looking at that.